In this video, we're going to review a couple key ideas from Chapter 4 to help you prepare for your final exam. In this first example, we're going to look at how an exponential function can be used to model some data. So we're given a table of data with some inputs and some f of x outputs. The first thing we want to do is show that indeed this function is exponential. So what we're looking for is a common ratio through the data. To show this ratio, we want to take some previous f of x value and divide it, we want to take the next f of x value, let's say 11.2, and divide it by its previous one, and make sure we get the same result throughout the table. So if I take 11.2 and divide it by 14, we'll see that we get 0.8. And if we were to continue that with the next piece of data, 8.96, and divided it by 11.2, you'll again see you get 0.8. So those ratios are continuing. If we take the next set, 7.168, and divide it by 8.96, we'll get 0.8. And lastly, if we take 5.7344 and divide it by 7.168, again we'll get 0.8. So this number here, this common ratio, we call that our growth or decay factor. To write the function, we would say f of x equals, if it's exponential, we take the initial value, or when x is 0, the initial value would be 14, times our growth or decay factor raised to the power of x. In this next question, it says, by what percentage does the function appear to be decreasing? We know it's decreasing because this number is less than 1. That growth factor typically comes from 1 minus our rate of decay. So I would say 0.8 equals 1 minus what number? Well, we took away 0.2. That is our rate of decay, but it's written as a decimal. We want it written as a percentage. So if I was to move that decimal place as 2 over, we would say that that is a 20% rate of decay. To find f of 7, if we know our f of x function, we can find f of 7 by plugging it in for x. So here f of 7 would equal 14 times 0.8 to the power of 7. So we're going to use our graphing calculator to evaluate this function. Following order of operations, we want to do 0.8 to the power of 7 first. And that gives us this number. Then we're going to take that number and multiply it by 14. So I would say f of 7, if we're rounding, let's say, to 3 decimal places, is 2.936. This next question looks very similar, but it's asking for something completely different. Here we want to know when this f of x value will equal 7. What x value would give us 7 for the function value? So we're trying to solve 7 equals 14 times 0.8 to the x. Now you could solve this by doing cross-graphing, but my suggestion, now that we have our knowledge from section 4.5, is that we can use logarithms to solve something like this. So to use logarithms, the first thing we need to do is get this exponential part by itself, so we're going to divide by 14. Now this is nice. 14 goes into, or 7 divided by 14, that reduces pretty straightforward to 1/2 or 0.5. If you're using logarithms, you don't necessarily have to do that. But since it does here, we'll go ahead and say that that's 0.5 equals 0.8 to the x. Now we can use our log properties. If we take the log of each side, we have this property that allows us to drop x in front and say log of 0.5 equals x times log of 0.8. So to solve for x, we're going to divide each side by log 0.8. Now we can use our graphing calculator because these cancel to evaluate this number here. So log of 0.5 divided by log of 0.8. And to 3 decimal places, we get x equals 3.106. Now I wanted to make a point about this. I could have left this number as 7/14. You don't have to reduce it or use it as a decimal. You'll get the same answer. And just to show that, if I was to do log, instead of 0.5, if I use the 7/14 here, and then divided by log 0.8, you would in fact get the same value. All right, so now that we know how to model exponential functions, let's look at using some percentages. This says a savings account earns 6.5% each year. Assume you have $50,000 in the account beginning January 1, 2015. Write a function for the account A of t as a function of years t. So the most important part here is that we develop a growth or decay factor. And since this is a savings account, I'm going to assume it's going to be a growth factor. And we know A equals 1 plus R in that case. If R comes from the 6.5%, as a decimal, I would say that's 0.065 if we were to move that decimal place 2 places over. So our growth factor A is going to be 1 plus 0.065. The growth factor is 1.065. So now I can write the function. A of t equals 50,000 times 1.065 to the t. Looking at our function, if we were asked what specific number tells us that the function will grow, this number here, our number that's raised to the exponent, tells us growth or decay. If A is greater than 1, we get growth. If A is less than 1, we get decay. In our case, A is 1.065. Since that number is greater than 1, I know that we're going to get growth. If you consider our previous example where A was 0.8, that's how we knew the function was going to decay. Let's say we want to find A of 5 and interpret its meaning in units. So to compute A of 5, that's telling us to plug in 5 for t. A of 5 equals 50,000 times 1.065 to the 5th power. Using our graphing calculator, I would do the 1.065 to the 5th power first to follow order of operations, and then multiply that number by 50,000. Now, since we're talking about money, an account, I would say round to 2 decimal places. So A of 5 equals 68,504.33. What this is telling us is that after 5 years, the account will be worth $68,504.33. What is the monthly growth factor for the account? Well, notice right now we have a yearly growth factor of 1.065. So we want to take 1.065 and turn that into a monthly growth factor. Anytime you want to take something and shrink its time period down, we want to do 1 over the number of new periods that would occur in the old one. So since we're going from yearly to monthly, and there's 12 months in a year, we're going to take 1.065 and raise it to the 112. We're going to use the TI graphing calculator. If you have a TI-83, you want to be a little bit careful here. When you raise this power, if you have an 84, it looks nice. It will all appear in the exponent. If you have an 83, you're going to want to use parentheses when you raise it to this power of 112. And we get this number, 1.00526. And so if we round that number to 3 decimal places, this growth factor will be 1.005. With this part over here, so that's our answer, but with this part over here, the 0.005, that's what R equals. And if I move that decimal place 2 over, in other words, this account is growing by 0.5% each month. All right, lastly, during what year will the account reach 100,000? So I'm going to use my function up here. What I want to know is when will A of t be 100,000? So we're trying to solve 100,000 equals 50,000 times 1.065 to the t. And again, here you could do cross graphing, but to me the easier thing to do so that you don't have to actually create the graph is to use logarithms. So we're going to start by dividing by 50,000. Which here works out nicely. If it doesn't, that's okay. You can just leave the fraction. But here it works out nicely to be 2. Then we're going to use our log properties. So we know log of 2 then would equal t times log 1.065. So t equals log of 2 divided by log of 1.065. Using the graphing calculator, log 2 divided by log 1.065 gives us 11.006, or in other words, about 11 years. Or 11.006 years, depending on how you're asked to round. And that's it.